This is a subject actually I've been wanting to present for some time. So thank you, Seven Signal, for giving me the platform to present on it. And what I wanted to do was, there's been a lot of discussion about Wi-Fi versus 5G private LANs. And I wanted to take a deep dive look at the physical layer. Because I really believe that the physical layer is how you really understand how a radio operates. I mean, the other layers are equally important. I'm not dismissing them, but I felt like let's take a really good look at the physical layer and what the implications are. So that's what I wanted to do today. Oops, there we go. Sorry. Why am I not? There we go. So that's a little bit of background of myself. You can read that at your leisure. Let's just move into the content. So what I wanted to do was to talk about the physical layer and how it impacts the operations of 5G in comparison with how a Wi-Fi network operates. I'm hoping it starts you on the path towards then looking at private 5G networks and how they might complement or even compete with your 5G, with your Wi-Fi network. And then at the end, I'm hoping that will give you pieces that you can start to evaluate how this might again fit in with your business strategy. So yeah, I've got one slide on why I think it's important to look at the physical layer. And then I've broken it into 3 sections where I'm going to discuss the physical layer. The first one is going to be around the signal itself. So it's an OFDM radio, just like Wi-Fi. And what does that look like? How different is it from a Wi-Fi network? So I have a few slides on that. Then I'm going to talk about the frequency bands. Now, in this section, I'm not going to talk about shared license versus license exempt or unlicensed. There's enough dialogue out there on that, but I do want to talk about the frequency bands and how the frequency bands are used and what the implications are of that. And then I want to talk about how we actually find and select the radio that we want to communicate on. And all of the slides are a straight comparison between Wi-Fi on one side of the slide and 5G on the other side of the slide. So you get a side-by-side comparison on all of the slides. And then I'll do a quick summary at the end. So my one slide on why the physical layer. So there's nothing more fun, I think, than understanding the physical layer. We often get, up on the higher layers because that's how we make the thing work, how it operates. But down at the physical layer is how we're actually sending our bits over the air. And if we send them in different ways, it fundamentally changes the type of things that we can do with it. And that's really why I wanted to bring it out. And it also shows what's possible and also what's not possible with these technologies. Now, remember, when I talk through this, I'm talking about what's defined in the standards. I'll point out some features that are actually been implemented versus future products. Just like with Wi-Fi networks, there are some features defined in Wi-Fi 6 that are not implemented. The same thing is true on Wi-Fi LANs, and that can make it difficult to compare and contrast this. So I'll try and point that out as I'm going through. Okay, so let's start then with the first of the 3 sections, which is the signal transmission. And as I mentioned, is OFDMA, so I want to talk about that. It's got OFDMA means it's got subcarrier spacing. So we're going to talk about that. We're going to have cyclic prefixes. I'm going to discuss modulation coding, so how it's modulated and coded to go over the air. And then I'll briefly touch on multi-user MIMO, which is also deployed in both technologies. So both technologies are OFDMA multi-user MIMO, but they are very, very different. So let's start with OFDMA. So when you look at cellular, when they defined 3G, there was a discussion by France Telecom and Vodafone over in Europe that said, hey, 3G should be OFDMA. And it was voted against, and everybody went towards CDMA. And the reason is that back in those days, they couldn't get EarthDMA to work, right? It was still very much theoretical in the labs kind of environment, early deployments. And so you don't see OFDMA happening in the cellular world until 4G comes along. And 4G defined subcarrier spacing of 15 kilohertz, compared with Wi-Fi, which was defined at 375, oh, I can't remember now, but 300 and something. It's very, very narrow subcarrier spacing. And the reason the difference is that cellular back then was looking at very large cells and vehicular speeds. And at vehicular speeds, you've got to worry about the Doppler effect. So large cells, you want to have smaller subcarrier spacing. Now, with 5G, they've said, hey, there's a demand for small cells. Small cells, we want to have larger subcarrier spacing. And so with the bands that are below 6 gigahertz, they've gone up to a 60 kilohertz subcarrier spacing. Now, up in the millimeter wave bands, they've gone to even greater subcarrier spacing, 120 and 240 kilohertz. But here in this presentation, I'm focusing on the sub 6 gigahertz band, which is where private 5G networks are being deployed. In Wi-Fi networks, you've seen in Wi-Fi 6 that they went to 1/4 of the subcarrier spacing and they dropped it down to 76. So you see both of these technologies are starting to converge. Both Wi-Fi and cellular have both realized that for smaller cells, high data rates, you're better off with EarthDMA and a subcarrier spacing roughly 60, 80 kilohertz. And they are close enough to really say that from a performance perspective, these radios will work very similarly. Now, what's been deployed today in our 5G LANs is all 15 and 30 kilohertz subcarriers. I haven't seen 60 kilohertz subcarriers being deployed. So it's in the standards, but it's not been deployed at this point, as far as I'm aware. Now, when you look at when you shorten up from a cellular perspective, when you increase the subcarrier spacing, what that means is you need to decrease the time interval. So one of the things that you see different in 5G is you see multiple subcarrier spacing, whereas in Wi-Fi 6 and Wi-Fi 7, you see that it's fixed. So in cellular, it's variable. And so your time interval is variable as well. So if you're using 15 kilohertz, you'd have a 1 millisecond time slot. 60, you'd go to 1/4, 0.25 milliseconds per slot. So when you're sending your modulation symbols, they're going to be shorter because your subcarrier spacing is wider. You're going to have shorter symbol periods, right? And so within this slot, in cellular networks, you typically send 14 symbols. So if you want your symbol duration, you have to divide these numbers by 12. There's also an option for 14, but 12 is the dominant one. Notice here is still symbol duration. And if you divide 12 into this, you get pretty close to the symbol duration in Wi-Fi networks. In Wi-Fi, you add the cyclic prefix. In cellular networks, this calculation includes the cyclic prefix, and you'll see that on the next slide. So the main thing you take away from this, both OFDMA, both transitioning to a very similar subcarrier spacing symbol duration time, right? Which is optimized for small cells. When you look at Wi-Fi networks, right, and here I'm looking at Wi-Fi 6, Wi-Fi 7 with the symbol duration, you see 3 different guard intervals, so that depending on your deployment, in smaller cells, you can use indoor, you can use a shorter cyclic prefix, which allows you to optimize your network. The same thing in cellular. And here I've given you the numbers, and again, we represent them differently. So sometimes it can be hard to compare and contrast. So, but here you can see this is my symbol duration, and here is my cyclic prefix. And you can see they are variable as well, depending on your RF environment. So if you were, what happens when you think about cellular like this, and this is, let's say this is a 20 megahertz band, in cellular, you might deploy some 15 kilohertz channels and you might put your voice traffic on those. And you might deploy some 30 or some 60 kilohertz subcarriers, and you would put, for instance, broadband data on those. And so in cellular, you have variable subcarriers within the same channel. In Wi-Fi networks, in a 20 megahertz channel, they would all be 78.125, I think it was, kilohertz subcarriers, right? And so in 5G, you see the flexibility to optimize your subcarrier spacing based on your service that you're offering within that channel, right? Something you don't see in Wi-Fi networks. And bear in mind, this is because the legacy in voice. When it comes to modulation and coding, no surprise, it's pretty similar, right? In Wi-Fi 7, you've seen them going up to 4K QAM. Not seeing that in cellular networks yet. You may see it in 6G, 7G, going up to higher modulations, but all of them are going to more bits per waveform. And the coders, you'll notice here, both of them use low density parity check coders, and these are optimized for high data rates. So you would use this if you were using a large resource unit, right? And a large size resource unit. For small resource units, which have not been implemented yet in Wi-Fi 6, you would use the binary convolutional coder. So if you're doing small resource units, right, small bits of data, you don't want to use the low density parity check coder because that's optimized for high data rates. So if you're going to use small resource units, low data rates, you want to use a different coder. Same thing in 5G, they use a polar coder and they use that for control and signaling, and all of their data goes on the low density parity check coder. So again, similar coding, similar modulation techniques. In actual fact, even though I call it a low density parity check coder, it's actually very, very different coder from the one used in Wi-Fi, but it's still the same concepts. That's a better coder for higher data rates. Use a different coder if you're down at the lower data rates. Same concepts, slightly different coding techniques. And MIMO, same thing, right? Wi-Fi 6 had 8x8 a multi-user MIMO, Wi-Fi 7 going up to 16x16. 5G LANs, again, the lower frequency bands using a 12x12 multi-user MIMO. Massive MIMO is defined in the millimeter wave band, so I'm not defining it here. That's why there's a difference. In later releases, we see it going up to 16x16, possibly. But again, very similar. Both of them are using multi-user MIMO techniques, both trying to push the umbrella to try and get beamforming to allow multiple users to transmit at the same frequency at the same time. Okay, so that was a little bit on the signal itself, for giving you some insights there. Now I want to go on to the frequency band, so our second section. And again, I don't want to talk about shared spectrum versus unlicensed. I really want to give you some glimpse into the bandwidth, the numerology that's used in 5G, because it's very different from Wi-Fi and it can confuse a lot of people. And I want to talk about carrier aggregation, right? Which we've done in cellular for some years and is now coming into Wi-Fi 7, right? So the numerology. So those of you, of course, most of you be familiar with Wi-Fi and our use of the actual band. And we actually talk about the band that the actual frequency relates to. And we also know that in these bands, you use TDD. So you're transmitting and receiving in the same frequency, right? in cellular world, in the sub 6 gigahertz band, that whole band from all the way up to 7.12 gigahertz is called FR1, frequency range 1. Frequency range 2 is up in the millimeter wave band. And then within that, we have these channel numbers. And notice here that these channel numbers overlap. How confusing is that? I shouldn't call them channel numbers, actually. I should call them band numbers. I'm sorry. Even I get confused. And so these are band numbers, and they're defined to support different countries around the world. So different countries have different amounts of spectrum available, and so you'll see these different band numbers, and that's all it means. And you'll see that where people in the States are deploying private 5G networks is band number 48. And you can see that that is overlapping in other countries, and that band is called something different. How confusing is that? And these, in the standards, you can do TDD, FDD, you can just transmit on the downlink, just transmit on the uplink, and this would be where you're pairing it with a different frequency band. And when we look at private 5G, it is all TDD, just like Wi-Fi, and it's operating here in the 3.5 to 3.7 gigahertz band, which means in comparison with 5 and 6, the coverage is greater for the same transmitted power, okay, than what you see in a Wi-Fi network where you're deploying a 2.4, 5, and potentially 6. So one of the reasons why 5G has greater coverage is simply because it's deployed in the lower frequency band when we're looking at private 5G. Now, when we look at the private 5G deployments, they are currently being deployed using a 10 megahertz channel. And some of you might be going, what, 10 megahertz, that's all? Because in Wi-Fi, you know, we think, well, 20 megahertz isn't very good. And we've been working on moving to 40, and of course, Wi-Fi 7 going up all the way up to 320 megahertz channels, you know, with all the bandwidth we now have in the 6 gigahertz band. So what that means is when you deploy a private 5G network, yeah, you have some coverage advantages, but your data rates are going to be a lot lower. Okay, so yes, it's more efficient use of spectrum, so that compensates for some of that, but you have significantly less spectrum, so your data rates are simply not going to be as high as was possible in Wi-Fi networks. Okay. So a lot of people are quite surprised when I show them the 10 megahertz channel. Now, when you look at that band number 48, it's broken up into these, where's my cursor gone? There it is, into these 10 megahertz channels is how it's typically displayed on slides, right? And you can see that there are 15 of these, and up to 7 of them, so there's actually 10, but up to 7 of them may be available for a license. And so you could see 7 of these in any particular space being utilized, right? And all the rest are available under what's referred to as the GAA license. Now, if PAL is not available, then theoretically someone could use all of this spectrum. Okay, so if you're deploying in an area like a port, where there's no other businesses, or in the countryside where you've got your factory and there's no other businesses out there, chances are you've got a lot of spectrum and you can aggregate multiple 10 megahertz channels together. And even if there's someone next to you that may have been allocated, let's say they've been allocated this spectrum here, you can aggregate discontinuous 10 megahertz channels. So yes, you've got 10 megahertz. And if you're deploying in areas that are very busy and you're surrounded by other people that are deploying 5G LANs, you may only have 10 megahertz. But if you are in a more remote area or you're more protected on an RF environment, indoors, something like that, then you can have availability of much more spectrum and you can aggregate it to get to much higher data rates. And the standards support up to 16. And of course, in this band, I only have 15 10 megahertz channels. And so that's why you're seeing some very high data rates in some of the private 5G networks. Okay. Similarly, in Wi-Fi 7, they're starting to aggregate channels together and aggregate channels across bands. One of the advantages you have of deploying a 5G LAN, if you work with a service provider, and I'm not encouraging you to work with a service provider, I'm just saying that if you do, a service provider has all their license spectrum as well as this shared band. And so that means is that not only gives you some opportunity for roaming, consistency, things like that, but it also means that that service provider can give you more spectrum and more services within your location in addition to your shared band. So one of the things to think about when you're deploying, do I want to deploy this independent of a service provider? Or are there some reasons that your business might benefit from having a service provider? Okay, good. Last section. So I'm doing good on time. That's good. So I wanted to give you some visibility. So we've talked about, hey, I'm EarthDMA. I've got cyclic prefix. I've got multi-user MIMO. I've got some advantages of 5G. I've talked about, hey, the bandwidth and some of the disadvantages of 5G. I wanted to talk now about how you find a base station compared with how you'd find an access point. I want to talk about resource blocks or resource units, okay? In cellular, we call them resource blocks. In Wi-Fi, we call them resource units. So I want to talk about that and what they look like. I mentioned that earlier. And I want to talk about how radio resources are allocated. So finding a base station or an access point. So as in Wi-Fi networks, as you know, you scan the RF looking for the beacon. And in Wi-Fi 6, 6 gigahertz got deployed, or Wi-Fi 6E, I should say. Finding channels in the 6 gigahertz required some new techniques. So you have things like preferred channels. Here I've illustrated that with these colored carriers. And you've got some other techniques as well to enable you to find the access point and what channels operating on in the 6 gigahertz band. You might think that's complex. It's nothing compared with how we do it in 5G. And this diagram I've got in 5G does not even indicate the complexity that you have in 5G. Because this is a shared or a licensed band, in Wi-Fi networks, right, you put pilot channels and they're evenly distributed in the frequency domain. In the cellular network, we have something called reference signals. And these are physical layer signals, just like pilot bits in Wi-Fi. And but we can vary them both in the frequency and the time domain. So over in cellular, you just vary them in the frequency domain, right? You've got different pilot bits at different frequencies, but reference signals can vary in the frequency and the time domain. And that makes the signals much more robust. And so what you do to find your base station in 5G is you have signals which are being sent at the physical layer only, so they carry no meaningful content, they're just known sequences of ones and zeros. You find the primary one, and that will be one of a small number of signals. So you say, oh, there it is. And once you've found that, your secondary signal follows immediately behind it. and that will be one of 100 and something odd. And so every base station will have a different combination of primary and secondary signals. And so you can distinguish between different base stations by finding this signal, right? So you find it, and immediately following behind these signals is a subset of your broadcast channel. And your broadcast channel tells you who the network name, right? So you know, hey, this is a service provider or this is a private 5G network. And then once you've found that, it'll tell you where to find the rest of the broadcast channel, right? So then you can find, everything you need to know. What subcarrier spacing is it supporting? What is your bandwidth? What multi-user MIMO streams are being used? Everything you need to know to connect to that base station will be in your broadcast channel, just like it's in your beacon in Wi-Fi, but it's actually this signal. You have to find it. And then again, this can vary if you've got multiple spatial streams. This can vary not only in the frequency of the time domain, it can vary in the spatial domain as well. And it can do all of that because it is a shared or licensed spectrum. You can't do that in an unlicensed spectrum. You can only do that and have that complexity in cellular. And again, this leads to the robustness, but also the complexity. What you should be walking away from here is, wow, cellular is really complex. But that's how it gets its efficiency and its performance level up significantly higher than was possible in an unlicensed band. It also makes it really difficult to deploy 5G in an unlicensed band where it is subject to interference. So this is good and bad, right? Okay, so that's really fun, isn't it? So again, both of them sending signals to help you find the base station, beacons in Wi-Fi, broadcast channels in cellular. Let's get down to our allocation of radio resources. Some of you might be familiar with this one over here in Wi-Fi, and you've got resource units. And as I mentioned, even though these smaller ones are defined, this is what's actually been deployed. And this is what I mentioned before. This is where you're using the low density parity check coders. And if you were using one of these, this is where you're down at lower data rates and you'd want to use the binary convolutional coder, right? But this hasn't been implemented, right, at this point. And so what you see here is the concept in Wi-Fi was to define small resource units. If you were sending small amounts of data, maybe an IoT device, and you would use a larger resource unit if you were doing broadcast data, right? So this is the concept that was defined in Wi-Fi 6. And a lot of people are hesitant to embrace Wi-Fi 7. You should embrace Wi-Fi 7, in my opinion, because a lot of optimization of using those resource units is in Wi-Fi 7. So, my personal view is start working on Wi-Fi 7 pretty quick. Because you'll want to leverage off those advantages. In cellular networks, we have resource blocks, the same concept, but we define them slightly differently. And a resource block is 12 subcarriers, right? So in Wi-Fi, the number of subcarriers per resource unit varies. It's different. We've reversed it in cellular networks, and you always have 12 subcarriers, but the size of your subcarriers is variable, and therefore the size of your resource block is variable. And as I mentioned, in a 20 megahertz channel or a 10 megahertz channel, I could have some small resource blocks, some big resource blocks. I would put my voice, low data rate, IoT applications here, and I would put my broadcast, maybe my low latency, because if I have a low latency application, if I give you more bandwidth, it takes less time to send it. So I might put my broadcast data or my ultra low latency services on a larger resource block. So same concept, but different ways of getting resource blocks, right? Or resource units, right? And again, same kind of concept, wanting to support different services that require different amount of bandwidth. Okay, and then when we look at allocating resources, so over here, oops, I've lost my cursor, there it goes. Over here in Wi-Fi, right, and you've probably seen these slides before, right, is when I allocate resources, and again, I'm simplifying it here a little bit because I do realize it's a little bit different on the uplink and the downlink, but I allocate resource units in time units. And here I've got an example where I'm allocating some resources to user 1, user 2, and user 3. And in Wi-Fi 6, you see some padding here where I'm not using that spectrum, and it's not very efficient, right? And this is scheduling mechanisms. And the reason why it's different in cellular is in cellular you have the concept of time slots, right? And so I can allocate every time slot, right? And so, as I mentioned, you have different time slots depending on what subcarrier spacing you're using. So if I'm using 50 kilohertz subcarriers, 36 kilohertz subcarriers, or 60 kilohertz subcarriers, my time slot is different. And each one of these would be sending a modulation symbol, i.e. with a cyclic prefix that we were looking at earlier. So each of these, you can see there's 12 of them, right? In this example, because I remember I told you there's typically 12 per time slot, 12 modulation symbols. So each one of these is carrying a modulation symbol. And you can see here, if I go to a 60 kilohertz subcarrier, my modulation symbol is going to be much smaller. I'm going to be able to send my data much quicker. And this is how we get to low latency in 5G. But bear in mind, only 50 and 30 kilohertz subcarriers has been implemented. 60 kilohertz subcarriers is still not implemented in private 5G networks, but this is possible in the future. This is how I get to ultra low latency. So what you should be getting away from this again is cellular more complex because of the variable subcarrier spacing. This is how it supports a multitude of devices, still supporting voice while supporting high-speed data. But the same concepts, it's just a different way of slicing up my spectrum. Okay. And again, much more efficient in 5G because I can use every slot. Okay. So that kind of wraps up the key physical layer attributes I wanted to share with you. So kind of give you a more instinctive difference of why these technologies are so different, right? And so now you can start making a decision with it. There are a lot of things I didn't discuss, right? I never discussed, I kind of alluded to the licensing issues. Cellular has a lot of interference cancellation techniques. These are, we've done interference avoidance in Wi-Fi for many years, and potentially you'll see new techniques coming into Wi-Fi down the road. Cell planning, I could have gone into that. A couple of things to note is that in Wi-Fi network, it just uses one very simplistic model. For those of you that have done 5G networks and IB wave, you'll be asked to choose your model, and you'll have different models for deploying outdoors, indoors, hilly environments, flat terrains, lot more model choice that you need to become familiar with over here. A lot more sophistication. Sectorized antennas are very common in cellular network to get my spectral reuse up much higher, because remember, I've only got a narrow amount of spectrum, so you're going to see a lot more sectorized antennas. And of course, there are very advanced frequency reuse techniques. Haven't seen them deployed in 5G LANs yet, but it allows me to start approaching a frequency reuse of 1. Again, it's possible in cellular networks. Haven't seen that techniques deployed in 5G. And I'll just explain it briefly. I shouldn't belabor this, but let's say you had two cells next to each other, you know, close to the base station, you can use all of your spectrum, and then you use a 1 in 3 on the edge of your cells. And you're like, wow, that's a sophisticated technique. Yeah, cellular's very sophisticated when it comes to using spectrum. So I haven't seen these advanced techniques, but there's no reason why they shouldn't be deployed in private 5G further down the road if we start running into spectrum shortage issues. So bear that in mind. Don't get too caught up. I mentioned reference signals and pilot bits. There are different ways, the same kind of concepts of looking at a received signal strength and signal to noise ratio. Slightly different the way you do it in cellular, so you need to know those different mechanisms and embrace them as part of your project planning when you're planning out your networks. And some of the advanced techniques that you see in cellular have come into Wi-Fi 7, like hybrid ARQ. We've been doing that since the dawn of digital cellular. So some techniques go to from Wi-Fi to cellular, and some techniques go the other way. And what you're seeing is a convergence of techniques at the physical layer on both standards, right? So just to wrap up, we've got 1 minute to wrap up, so perfectly on time. Wi-Fi networks, lots of fantastic spectrum, high data rates. If you're working in an environment where you can protect your RF like factory floors, Wi-Fi is amazing. You can get to really high data rates and lots of throughput. Lots of devices out there, they're clearly dominant, and lots of IoT devices starting to emerge in the market as well. Widely understood, and you're starting to see better support for IoT. I think Wi-Fi 7 and the IoT things are very important for the success, long-term success of Wi-Fi. 5G is really interesting, and I encourage anybody to look at it. The main reason is reliability. I can guarantee your voice. I can guarantee your IoT on your factory floor. You just can't do that in Wi-Fi networks. Better coverage because of all the techniques like lower frequencies, sectorized antennas, all of the managing my spectrum much closer, interference cancellation techniques. All of those techniques result in a greater coverage for the same transmitted power. Communications are private. Largely it's considered 5G is more secure than Wi-Fi. I'm not going to get into that here. Perhaps another webinar at another time. Consistent performance and your IoT is proven in IoT. It does work for IoT and voice. So with that, I've talked about the physical layer. I'm just going to give the certification course that's available on CWNP a quick plug, that if you want to come in and learn more, then please go ahead and do that certification class as part of doing your other Wi-Fi certifications with CWNP. And with that, I have finished, and I can hand back to 7 Signal.
That was perfect timing. Awesome. Well, thank you so much. Already getting tons of great comments, feedback from the session. So thanks to you, Dr. Avril, for joining us. And we do have a few questions. And some of them, this is a real treat for us because we don't get to talk about private cellular a lot on these sessions. It just doesn't come up. So it's a treat to learn about that. And we do have some questions kind of revolving around that. So from Forrest, he's got 2 questions. One was from kind of earlier in the session, but I wanted to hold out in case that got answered. And I think you touched on it a little bit, but some of it is revolving around the fact that we don't hear about private cellular a lot in these sessions. So 2-parter here. So Forrest says, you just said 5G LAN, but I was thinking 5G is communication between clients and cell towers. Can 5G be used in households with 5G APs from Walmart?
Yeah, so all of you probably, well, not all of you, I've had played with a 3G femtocell and a 4G femtocell. I haven't got a 5G femtocell, but I've played with those and deployed them in my home quite a bit. And so absolutely, there's no reason why this couldn't be, service providers can deploy femtocells to give you better cell coverage in your business. And you can also deploy them in the home market. Now, I'm not aware of, there's no private 5G in the 3.5 gigahertz band that I've seen currently going after the home market. So
Mhm.
that band itself is all looking at uh, enterprise deployments or neutral service providers. So like Comcast, if they wanted to deploy cellular-like type services in sports arenas, they can deploy a 5G LAN. So no, we're not seeing it in the home market in the band. So if private 5G means to you 3.5 gigahertz band, then the answer is no. If 5G means to you a technology that can be deployed in the home, then yes. So two answers to the same question.
Perfect. Awesome. Thank you. And then Forrest kind of asked just an overall general question too. Why draw the comparison between 5G cellular phone service communication and Wi-Fi if it's not Wi-Fi at all?
I think that's a fair point, and I think the answer to that, I'm just going to draw it here, is
Mhm.
that let's say you've got an enterprise, right? And they've deployed Wi-Fi, and they've deployed Wi-Fi right across their business, but they're now wanting to have reliable voice, and they're not able to do that in the Wi-Fi network. Or they need to have a factory that's got reliable IoT, ultra low latency. Those things, 5G is providing an alternative. And this is where we get into does Wi-Fi compete or complement? So all the vendors tell you that these complement each other. But the reason I took you through the physical layer is because absolutely they compete. From a technology perspective, there is overlap. If you think about the services that you can do in Wi-Fi and the services that you can do in 5G, yes, there's some like reliable voice and low latency IoT that you can only do in 5G. And there's broadband unreliable data that you can only do in Wi-Fi. But there's a lot that overlaps and competes. And so the reason I did this comparison was because in the enterprise, there are a lot of people saying, does it make sense that I do 5G LANs? Where should I deploy it? How do I fit them? And I think by looking at the physical layer, in my opinion, you get a better kind of ground up view as to where these technologies might fit in the enterprise. And that was really what I was trying to give you. So hopefully I achieved that. So yeah, let me know, Forrest.
Yeah, Forrest says thanks. And we got another just comment thanking you for really getting into the fundamentals of this concept. It's great for people breaking into this industry and this good old technical stuff. So thanks for that. Got one from Andrew. A big problem for me in OTRF is roaming times. How quickly can private 5G LANs roam from one cell to another typically?
So I'm trying. Okay, so that's an interesting question. So I believe the standards define it at 50 milliseconds, and that's defined for voice. However, one of the things that's different for cellular, which is why I think I wanted to, which is why I said there's not such a simple question. So in cellular networks, and I'm not saying you're doing this in private 5G at this point in time, right? But I can simultaneously transmit and receive from two base stations at the same time. And so if you're thinking, hey, if it's spec'd out at 50 milliseconds and I'm a factory device, how much data will I lose during this time? Because this was really spec'd out for voice, right? The techniques in cellular will allow you, in theory, not to lose your connection at all because you can transmit and receive at the same time from 2 different base stations. So you'll be talking to one here, your transition to 2, and then your transition to 1. So in that sense, I would argue that your roaming time is 0. Right? So your definition of roaming is different in cellular networks. Well, that's why we talk about handoff and handover and simultaneously transmitting at the same time.
All right. Okay, so here we go, guys. Inside 7 Signal, we've got our Wi-Fi 6 sensor out there. There's the Sapphire I6200. And the 6200 is Wi-Fi 6 enabled, and it's already starting to capture some of this OFDMA frames in the air flying around, as you can see in this location. So we're measuring OFDMA in the download direction here, the airtime utilization. We're measuring it in the upload direction, as you can see here. Very few frames, as you can see by the decimal point here on the y-axis. Nevertheless, it's in effect. And then, of course, total OFDMA airtime utilization. So why is this important? It's important because we want to make sure that we're getting the most out of our investment. A lot of us are thinking about upgrading our entire enterprise infrastructure to Wi-Fi 6, whether that be the Cisco 9100 series or whatever it might be. And we just want to make sure it's like, okay, once I make this investment, am I going to be able to take advantage of OFDMA and the resource units and the channel sharing that hopefully will result accordingly, making my entire Wi-Fi network more efficient and allowing users to have better experiences. So it's important to measure. And that's what we're doing right here with the Sapphire I. We're measuring what is going on, and we can't manage anything that we don't measure. So there you have it. Now let's move on. Let's move on to Mobileye. So in Mobileye, we have the ability to basically take an inventory of your client device population. And in doing so, we are able to see, okay, how ready is my fleet for Wi-Fi 6? I mean, some organizations, they don't upgrade their laptops for many years, 4 years, 5 years. And so what is the point of upgrading one if I don't upgrade the other? I want to make sure that this is coordinated, where my device population and my Wi-Fi infrastructure refresh are kind of meeting up at the same time. And they're able to achieve, the maximum power of that. So when I look at a chart like this, guys, I can actually see, wow, here's an environment, a customer, where I can actually go around the ring here and I can see, okay, the majority of these devices are still on AC. Actually, there's a whole lot of variation. Look, there's so many different types of adapters that are in this environment. So this could be rather, frustrating from the standpoint of, what am I going to do? What am I going to do? Do I upgrade now or do I upgrade later? Let's look at another one. Let's look at this one. This one, very little variation. When I mouse over this right here, 1,700 devices using the Wi-Fi 6 adapter. Not a lot of variation when you look at the sunburst. Now, what I did is I exported these and I wanted to break it out with a pivot table in order to better illustrate what's going on. So here you have it. So organization has thousands and thousands of laptop computers all over the world, all over their enterprise. I want to be able to quickly and easily see, okay, is my fleet of devices ready for Wi-Fi 6 or not? Can I push off the upgrade just a little bit longer or not? Information like this is going to help inform our decision making. So as you can see right here, I've simply highlighted in yellow the different Wi-Fi 6 adapters that we see out there in our field. And of course, I'm able to compare that to all of the different variations. I even have some N adapters out there as well. As you can see, these are some pretty old ones. A lot of AC out there. You can see the counts in column B. I've got another one I want to show you. Let's look at this one. This is the one. This is the table where there's less variation. Remember, I showed you the sunburst where there was a lot less variation. So here we're talking 5,000 devices here. And look at this. You can say that the majority of those 5,000 devices are Wi-Fi 6 capable. And so, one might argue that when we look at our device inventory, we're more ready to take advantage of an upgrade of our Wi-Fi infrastructure to Wi-Fi 6 because the devices are ready. So there you have it, guys. There you have it. Using 7 Signal in order to help inform your decisions. You know, knowledge is power. And I just want to remind you guys out there that while you and me, we can't see or hear Wi-Fi, but 7 Signal can.